4.1 Extreme Values of Functions. The outline of this video is as follows. We will discuss a systematic way to find the highest and lowest values of a function. I will begin by defining absolute or global extrema, which represent the overall maximum and minimum values across a function's entire domain. Then, I will introduce the extreme value theorem, a key result that guarantees these values exist under specific conditions, namely for continuous functions on closed intervals. After establishing the global picture, I will define local or relative extrema, which are the smaller peaks and valleys you might see along the curve. To tie it all together, I will explain the crucial concept of a critical point, showing how these special points, along with endpoints, are the only places we need to look to locate all types of extreme values. Let us begin by defining the absolute extreme values of a function, which are simply the highest and lowest points it reaches across its entire domain. A function has an absolute maximum value at a point C if its output, f of c, is greater than or equal to its output for all other x values in the domain. Conversely, it has an absolute minimum if f of c is less than or equal to all other function values. For example, consider the function f of x equals cosine of x on the closed interval from negative pi over 2 to positive pi over 2. Its absolute maximum value is 1, which occurs at x equals 0. Its absolute minimum value is 0, which it reaches at two locations, x equals plus or minus pi over 2. Notice we distinguish between the extreme value itself and the point where it occurs. The essential idea is that absolute extrema are the single highest and lowest outputs a function can produce. The existence of an absolute maximum or minimum depends critically on the function's domain, not just its formula. Let us explore this using the simple function y equals x squared. When the domain is all real numbers, the familiar parabola has an absolute minimum of 0 at x equals 0, but no absolute maximum because it increases without bound. If we restrict the domain to the closed interval from 0 to 2, we now have both a minimum at x equals 0 and an absolute maximum of 4 at x equals 2. However, if we exclude the left endpoint, on the interval from 0 up to and including 2, the function gets infinitely close to 0 but never reaches it, so it loses its absolute minimum. Finally, on the open interval from 0 to 2, with both endpoints excluded, there are no absolute extrema at all. The essential point is that the function rule alone is not enough. You must always consider the specific domain. After seeing that extreme values do not always exist, the extreme value theorem provides a crucial guarantee for when they must. The theorem states that if a function is continuous on a closed interval from a to b, then it is certain to achieve both an absolute maximum value, capital M, and an absolute minimum value, little m. This means there are points in the interval where the function's value is exactly m and m, and for all other points x, the value of f of x is between m and m, inclusive. The two key ingredients are essential. The function must be continuous, meaning its graph is unbroken, and the interval must be closed and finite, meaning it includes its endpoints. If either condition fails, the guarantee is lost. The essential thing to remember is that continuity on a closed interval is a sufficient condition for absolute extrema to exist. To find the absolute highest or lowest value of a function over a specific interval, we have a very powerful shortcut. We only need to check a few special locations. The first type of location is an endpoint, which is simply the start or end of the interval we are examining. As you can see in the graph, the absolute maximum value, capital M, occurs at the right endpoint. The second type of location is an interior point, meaning any point between the two ends. Here, the absolute minimum value, small m, is found at an interior point. Imagine you are looking for the highest altitude on a road trip from Denver to Salt Lake City. The highest point might be a mountain pass along the way, which is an interior point, or it could be one of the cities themselves, which are the endpoints. So the key idea is that an absolute extreme value must occur at either an interior point or at one of the endpoints of the domain. Now let us narrow our focus from the overall highest and lowest points to what we call local or relative extreme values. A local maximum occurs at a point C if the function's value, f of c, is greater than or equal to the values of f of x for all x in some small open interval around circa. In simpler terms, it is a peak in its immediate neighborhood. Likewise, a local minimum is a valley, a point lower than all of its immediate neighbors. For instance, in a mountain range, every individual peak is a local maximum, but only the tallest one is the absolute maximum. This means that an absolute extremum is always a local extreme as well, since the highest point overall is certainly the highest point in its own local area. The key idea is that local extrema are all the peaks and valleys on the graph, not just the single highest or lowest one. This theorem provides a powerful and direct method for locating potential local extrema by connecting them to the first derivative. The theorem states that if a function has a local maximum or minimum at an interior point C, and if its derivative exists at that point, then the derivative at C must equal 0. To see why this is true, imagine a smooth hill that represents a local maximum. The slope of any line approaching the peak from the right is non-positive, while the slope of any line approaching from the left is non-negative. For the derivative to exist as a single, unique value at the very peak, it must be the one number that satisfies both conditions, which is 0. This same logic holds for a local minimum at the bottom of a valley. Therefore, to find potential locations for smooth local extrema, we search for points where the function's derivative is 0. To find a function's extreme values, we do not need to check every point in its domain. We can narrow our search to just a few specific locations. Based on what we have learned, extrema can only occur in 3 places: at interior points where the derivative is 0, at interior points where the derivative is undefined, or at the endpoints of the domain. I will group the first 2 types of interior points together under a single important definition: a critical point. A critical point is any interior point where the derivative is either 0 or undefined. However, you must remember that a critical point is only a candidate for an extremum, not a guarantee. For instance, the function y equals x cubed has a derivative of 0 at x equals 0, but it has neither a local maximum nor a minimum there. So, the complete list of candidates for where any extreme value can be found consists of all critical points and all endpoints. I will now show you a reliable, 3-step method for finding the absolute maximum and minimum values of a continuous function on a finite, closed interval. First, you need to identify all the candidate locations, so find every critical point of the function that lies within the interval. Second, make a list of the function's output values by evaluating the function at each of those critical points, and also at the 2 endpoints of the interval, which we can call A and B. It is very important not to forget the endpoints, as the highest or lowest value often occurs there. Finally, simply look at your list of values. The largest value on your list is the absolute maximum, and the smallest value is the absolute minimum. This simple procedure of checking critical points and endpoints guarantees you will find the function's absolute extrema. Now we can put our method into practice by finding the absolute extreme values for the function f of x equals x squared on the closed interval from -2 to 1. First, we find any critical points by taking the derivative, which is 2x, and setting it equal to 0. This gives us a single critical point at x equals 0. The next step is to evaluate our original function at this critical point and also at the endpoints of our interval, which are -2 and 1. Plugging in these three x values gives us a set of candidate values. F of 0 is 0, f of -2 is 4, and f of 1 is 1. Finally, we simply compare these results. The largest value is 4, so that is our absolute maximum. And the smallest is 0, which is our absolute minimum. This example highlights a crucial point. The absolute maximum occurred at an endpoint, not at the critical point, which is why we must always check the endpoints. Now let us apply our method to find the absolute extrema for the function f of x equals 10x times the quantity 2 minus the natural log of x on the closed interval from 1 to e squared. To find the critical points, we first calculate the derivative, f prime of x, which simplifies to 10 times the quantity 1 minus the natural log of x. Setting this derivative to 0 gives us our only critical point inside the interval, which is x equals e. Next, we evaluate the function at this critical point and at both endpoints. At the left endpoint, x equals 1, the function's value is 20. At the right endpoint, x equals e squared, the value is 0. At our critical point, x equals e, the value is 10e, which is approximately 27.2. By comparing these three results, we find that the absolute maximum is 10e at the critical point, and the absolute minimum is 0 at the right endpoint. Here I will show another way a critical point can arise, which is when the derivative is undefined. My function is f of x equals x to the power of 2/3, and I want to find its absolute extrema on the closed interval from -2 to 3. First, I find the derivative, which is 2, divided by the quantity 3 times the cube root of x. This expression can never equal 0 since its numerator is a constant 2. However, the derivative is undefined at x equals 0, because that would lead to division by 0, making 0 an interior critical point. Now I evaluate the function at this critical point and at the endpoints. The function at 0 is 0. At the endpoint -2, the value is the cube root of 4, or about 1.59. At the endpoint 3, the value is the cube root of 9, or about 2.08. By comparing these results, the absolute minimum is 0, and the absolute maximum is the cube root of 9. Remember that a critical point can be a place where the derivative is 0 or where it is undefined. Let us bring everything together by reviewing our complete strategy for finding the absolute extreme values of a function on a closed interval. We started with the extreme value theorem, which gives us a crucial guarantee. As long as a function is continuous on that interval, we know an absolute maximum and minimum must exist somewhere. Next, we learned that these extreme values can only occur at very specific locations. These locations are either the endpoints of the interval or interior points where the derivative is 0 or undefined, which we call critical points. This insight provides a simple and powerful method. To find the absolute extrema, we just need to identify all the critical points and the endpoints, evaluate the function at each of these candidate points, and compare the resulting values. The largest value from this list is the absolute maximum, and the smallest is the absolute minimum. Let us apply our method to a couple of review questions to see how the conditions for absolute extrema work in practice. First, consider the function f of x equals 1 over x on the interval from 0 up to and including 5. The key here is to check the requirements of the extreme value theorem, which guarantees an extreme only for a continuous function on a closed interval. Our interval is not closed because it excludes the left endpoint, 0. As x approaches 0 from the right side, the function 1 over x increases without any limit, so it has no absolute maximum. For the second question, we have a function g, whose derivative is given by x times the quantity x minus 2. The critical points are where this derivative equals 0, which occurs at x equals 0 and x equals 2. Therefore, to find the absolute extrema of g on the closed interval from -1 to 3, we would need to evaluate the function y at these two critical points and also at the two endpoints, -1 and 3. The absolute extrema must occur at one of these four specific points.